Okay, let's get started. Welcome to lecture 5, so halfway through. And because we're halfway through, I'm going to switch gears a little bit. So last 4 weeks, we talked about basically different kinds of light you might want to see. And now we're switching to basically stuff that astronomers look at that isn't really light. And we're going to start with cosmic rays. And if you're like me and you've been a physicist in Germany talking about cosmic rays, you're obliged to start with this guy. This guy specifically, Victor Hess. And you can see he's in a balloon. And the reason why he's in this balloon is because it's the early 1900s. And people had more or less just discovered radioactivity. So they recognize that there's certain, mostly rocks, that give off this radiation. It's called ionizing radiation, because what it does is you can have a particle, this can, for example, be an electron, kind of bump into one of the electrons in the shell of an atom, and then it will just knock this electron out of the shell. And that can do several things. So one thing it will do is, if you have a photographic plate, it will turn this dark. So this is how radioactivity was discovered. Someone just more or less by accident had a piece of uranium lying on a photographic plate and realized that for some reason got darkened. It also, if this happens to, for example, like in one of your cells, you kind of have a bit of a problem, because this atom is going to want its electron back, and it's not really picky where it gets it from. So it becomes really, really reactive, and if that, for example, happens in your DNA, that can cause all kinds of problems. But what also happens is that now you have this free electron here running around, and if this happens in a gas, for example, this electron can kind of move more or less freely, and so the air becomes a little bit conductive. And this was kind of how the first, or some of the first radiation measurements were done, with something called an electroscope. So this is actually one of the electroscopes that Victor Hess used, and this is a sketch of a very similar one. So what you do is you have a little kind of like a metal kind of leaf thingy, so a little metal strip, and then you just kind of put a bunch of charges on there, and because equal charges repel, the tips of this strip, or the middle of it, will kind of move apart a little bit. Then you have a microscope here where you can see it, and what you watch is basically how quickly does this move back together. So how quickly can the charge move away or move out of this little metal strip, because that tells you how conductive the air is, and that tells you how much radiation there is. And so what Victor Hess did was so the idea was, we have all these rocks that are radioactive, and they're pretty much on the ground. So if we move further and further away from the ground, we should see less of this radiation. And people started just kind of climbing on whatever high buildings they had available at the time. And actually, the radiation decreased a little bit. But Victor Hess decided, well, I can do one better and just get into a balloon. And these are his notes from one of these balloon trips. This says his balloon was filled with hydrogen, so he was kind of brave. But so this is, it's in German, sorry. So this is the altitude in meters. And this is relative to ground, and he had these two radiation measurement devices, these two electroscopes. He also had a third one, but someone bumped into it, so it kind of stopped working halfway through. And it kind of, when he lifted up, it stayed more or less constant, and then when he got up to like around 4,500 meters, or 5,800 meters, suddenly he saw more than double the radiation he saw before. Yes?
For those of us that don't speak German, I notice you have Strahlung, Holy Strahlung, and in past lecture series on X-ray astronomy, we've been exposed to different kinds of Strahlungs. And there's this Strahlung and that Strahlung, and so what does Strahlung mean, and how do you hook it together with the first part? Up there you got Baubach-Tete Strahlung. What does that mean?
Okay, well, this just means observed radiation. And this is, so Höhe is altitude, and Strahlung is radiation, so it's altitude radiation, because at the time, this is what Victor has called it, because at the time, that's all he knew. There was some kind of radiation that you see when you're at altitudes. Now we call this cosmic rays, if we speak English. But this was at the time, so this was kind of the first observation that you have some kind of radiation that's apparently coming from above, or that's at least more common the further up you are. But with these electroscope, really all you could measure is kind of, like how much radiation do you have on average. So fortunately, this guy, Charles Wilson, soon came up with a better detector, pretty much by accident. What he was actually looking into was how clouds form. So he had this cloud chamber where he just had water vapor, and he tried to get it to like a humidity and pressure where clouds would form. And he noticed that when he just kind of got just to this point where clouds would start forming, you can see these little streaks moving here. So this is one of these cloud chambers. Today, usually if you build them yourself, you use alcohol. And someone put a piece of uranium in the middle just to kind of make it more dramatic. And you can see that there's these little streaks moving out. And that's because you have this ionizing radiation. And these ionized atoms that you get, this can cause clouds to form. And now you cannot just measure the absolute or the average radiation anywhere, but you can see like individual particles moving through there. And this was actually really important for kind of the early days of particle physics, because this was before particle accelerators were really invented, so you had to kind of race for free. And this was also at the time when quantum mechanics was starting to get figured out. And one physicist, Paul Dirac, came up with an equation that seemed to work really well. But it also predicted that there should be a particle that acts like an electron, except it has a different charge. And so Carl David Anderson just tried to look for this in this cosmic radiation. And what he did was he first of all put a magnetic field around this cloud chamber. And so in a magnetic field, these particles will be deflected depending on the charge. And then to figure out which direction the particle is moving, he put a lead plate here. And the idea is that if you have a particle moving through this lead plate, it's going to lose some energy in this. And so you can just check where the particle has more energy, which you can see by how much it is deflected. So the deflection will depend on the charge and the energy. And he saw that there is this particle coming in this photo from here. And you can see after it's passing through the lead plate, it gets deflected more. So it lost some energy here. And from the direction it's moving, you can see that it has the opposite charge of an electron. So in principle, it could be a proton, but a proton would actually leave a much, much larger trail here. So the trail itself, like the thickness of the trail, looked more like an electron. So this looked like this electron with an opposite charge, which now we call a positron. And he got a Nobel Prize for this, together with Victor Hess, interestingly. And so particle physics was in a really nice state where you had all, you knew every particle, you knew what it did. And then the same year he got this Nobel Prize, in 1936, he saw this. He saw this particle that moves through there and gets a little bit deflected, but hardly. And it looked basically like an electron, but it was heavier. And now we know that this is something called a muon, which is almost exactly the same as an electron, except it has a bigger mass. And this was kind of a big deal in particle physics, because suddenly you had this particle that no one really knew where it came from. No one really, it didn't make sense at the same time, but this then started actually a bunch of other discoveries. But yeah, this was kind of how particle physics got started. The problem with these kind of detectors is that you have to have someone watch it with their own eyes, or you can take a picture from it, but you're not really getting an electric signal or anything. You cannot kind of do if you want to build a detector, you kind of want something that you can just leave running and it will kind of trigger itself. So for that, today there's different techniques. One that's really popular is something called scintillation. And the idea is that if you have this ionizing radiation moving through a material, and certain materials, what will happen is it will not only ionize part of the material, it will also excite some of the electrons in the shell of the atom. So then it will do this, what we talked about a couple of weeks ago, when we talked about emission and absorption lines, it will have electrons moving between different orbits in the atom, and that will emit faint light. And so that's also used at particle colliders. So this is one of these scintillation detectors that's used at ALICE, which is one of the detectors at the Large Hadron Collider. For cosmic rays, you often have something like this. So this is for a cosmic ray detector. You have these plates here that are covered with some shielding material to shield it from light from the outside. But there's a scintillation crystal here, and then you have these fiber optics that will then lead the light to somewhere where you can detect it. It's interestingly also something that you kind of sometimes see in very expensive watches, where you want them glowing. So you have sometimes you have a little bit of tritium here, which is a radioactive isotope of hydrogen. And then you have a little scintillator around it, and that way you always kind of have a little light on your watch and can even read it if for some reason you're in the dark for 3 days or something. So now you have a tiny flash of light when a particle runs through there. But now you also, light is all good, but you want to convert it into some electrical signal. So what you use for that is a photomultiplier tube. So they kind of come in different sizes and shapes depending on what you need. And the way they work is they use something called the photo effect, where if light shines on certain metals, it can also knock an electron out of this metal. And then you have a single electron that's going to be pretty hard to measure. So what you want to do is you want to turn one electron into many, many electrons. So what you do is you apply a very strong electric field between the metal plate that the electron came from and some what's called a dynode, which is just basically a metal plate. And so then this metal plate is going to attract the electron, and the electron is going to slam into this dynode, and that's going to knock out more electrons out of this metal plate. And then you have an even stronger electric field that goes from one dynode to the next. So now these electrons that you just freed from there are going to slam into this one and knock out even more electrons. And then you just repeat this a bunch of times, and every time you get more and more electrons. And at some point, if you do this enough times, you have a current that's strong enough that you can measure it. And then you just have a little readout here that then tells you what the current is, and that's going to be proportional to how much light you started with at the start here. But now you don't take only one of these, you take two, and you build what's called a coincidence detector. So you cable them up so that you have two of these photomultipliers that then have a scintillator attached to it, and you wire them up so that you combine the signals from two of them. And then only if both of them send you a signal within a very short time frame, then you actually send a signal further on. So what you're looking for is if two of your detectors get triggered or get hit at the same time. And people did this in the late 30s. They used Geiger counters, not scintillators, to be perfectly accurate. But they noticed that actually how many of these coincidences you see depends on how far apart your detectors are. And you can also calculate that if all these rays were not connected to each other, how often would I expect to just kind of by pure coincidence see two particles hit my two detectors at the same time? And if you do that, you realize that actually you see a lot more coincidences than what you would expect just by pure chance. And from this you can see, like, even if you move something like 100 meters or several hundred meters away, you can still see more coincidences than you would expect. Yes?
So is the idea that it's the same cosmic ray going through both detectors, or that there's a pack of cosmic rays going through?
That's what I'm getting to now. Yes, because the second one. Because the way to explain this is kind of, if you want a very simple model, you use something called the Heitler model, where you have your cosmic ray that's coming from space. It's hitting the atmosphere, and it's going to move through the atmosphere a little bit, but at some point, it's going to hit some atom there, some nitrogen or something. And that's going to produce some new particles, and then they're going to move through the atmosphere. They're going to hit another particle and produce even more. They're going to hit more particles and produce even more, and so on. And then you have this big shower of particles. Now, this is going to continue until at some point, because you have some initial energy, but that gets split between all these new particles you create. So at some point, each individual particle here is going to have not enough energy to create new particles, because you need a certain energy to create particles. And so then the shower is going to stop. And that's why and then these particles are going to continue, but they're going to lose energy just from, for example, ionizing the air. So that's why you see more of this radiation further up, because that's kind of when you have all these particles developed, but they haven't been, this shower has reached its maximum. And actually, if you go even higher with your radiation counter, you would actually see less radiation at some point, because you're kind of above where most of these particle showers have formed. Now, this is a very simplified model. In reality, it looks a lot more complicated, because you don't necessarily just create two new particles. You can create a bunch of new particles at once. You can create different particles. Some of them are going to decay, and it's all kind of complicated. But we know how particle collisions work. That's something that people in Geneva or here at Fermilab have been doing for a while. So we can actually simulate pretty well how the shower would look like. And this is an example for a very high energy shower done with a software called Corsica. So you can see here, this is where the initial interaction is, and then you have these particles propagating, and at some point you have this kind of maximum where you have a lot of particles, and then the shower is slowly dying out. Now, the nice thing about this is if you want to detect this, because really what we want to see is, we want to figure out we want to learn about this initial particle that caused all this. So if you want to kind of detect that there was a shower, you don't actually need to detect every single particle here, right? You can just kind of detect a few of them, realize that they're all coming at the same time, roughly from the same direction, and then you can you kind of get a subsample of all the particles in the shower instead of just measuring them all. And so what you can do then is you can build experiments like this. There's one called the POG Observatory, which is in Argentina, literally in the Pampa. La Pampa is the region where it is. And there's the telescope array, which is in Utah, like 2-hour drive from Salt Lake City. And these are huge. So POG Observatory is about the size of Rhode Island. So it's like 3,000 square kilometers. Telescope array is a little smaller, but also like I think it's like 1,700 square kilometers. And then the detector itself, looks like this. So for the POG Observatory, so for the telescope array, you just have this thing here. So this is one of these scintillator plates. And then you just have a solar panel for power, and here's a little antenna to kind of send the data to some computer somewhere. POG Observatory works a little bit different. This is basically water tank, because particles going through water will also emit light. We'll talk about how this works in a week, because I don't want to talk about detectors all day today. Is that a question?
Yes.
Oh, okay. You go first.
Are these like sort of scattered all over the place, or is this just from really far back? And those things are like, and that's like the individual thing is huge.
Yeah, so this is one of them. So for the size, a POG Observatory, because it's in the Pampa, it's kind of a running gag to have cows in the picture for size. So this is how big it is. For TA, unfortunately, I didn't find any cows. You have to do with people. And so this is a map. So each one of these dots here is one of these tanks. And between them, it's about 1.5 kilometers, so a little under a mile. So it's, these are fairly simple, but it's like cover a huge area. Yeah.
I thought I heard you say a 2-hour drive from Salt Lake City. Is that what you said?
Yeah.
It's southeast. I've been there. Those things they're amazing. There's a road called the loneliest road in America, and you can drive for an hour without seeing another human being. But you see these things every half mile or so. And they're in the distance as far as you can see.
Yeah, I haven't been there myself. I was just curious and looked it up on Google Maps, to be honest. And so with these, you can detect these particles from these air showers. And now we want to know, basically, based on how many particles we detect, what energy did this shower have, does it look like. And so ideally, we would actually want to see the shower itself. And you can do this with these things. So at the Pure Geo Observatory, there's one of kind of these telescopes at each of these ends. So there's one here, one here, one here, and one here. And the way they work is that actually nitrogen is also a scintillator, and the air is mostly made up of nitrogen. So if you have one of these showers moving through the air, it will also emit a very faint light because air is not very dense, so the light is going to be a lot fainter than if you have a more dense material. But if you have a really good telescope, you can actually see this light shimmer. So inside of this building, behind kind of each of these doors, you have a mirror here that looks kind of black because it's dark in there. And then you have a bunch of these photomultipliers here. So if there is a particle shower in the air, it will emit light. These mirrors are going to reflect it into these photomultipliers, and then from the light you can figure out what the shower looks like. The problem with these is that this light is really, really faint, so you can only do this in really, really dark nights. So if you turned this on, even if there was just a full moon, you would break your detector. Like these photomultipliers would just basically explode. Probably not explode, but definitely break. And so this is what an air shower looks like from these telescopes. So the bottom and the top are each from a different telescope of these. And the nice thing about these photomultipliers is they give you really good timing information. So the color here tells you kind of at what time this was detected. So the red color means it was detected later than the green part. And so you can actually, with these telescopes, you can actually see the shower move down. And from the amount of light that was emitted, you know how much energy this shower dumped into the atmosphere. And from that, you can figure out the particle of the initial cosmic ray that caused all this. Yeah?
Can you calculate the structure of the umbrella, the structure of by the starting energy?
You mean like the width of the shower? Yes, you can. It's a bit more complicated. I can get into this in a little bit. Now, as I said, the problem with these is, these only work in really dark nights, about 15% of the time. So this, what you can calculate then is basically at what position along the shower how much energy was dumped into the atmosphere. And you usually write this down in these weird units that basically tell you kind of how much atmosphere was crossed, because that actually explains the shower much better, because the upper part of the atmosphere is going to be a lot less dense than the lower part, and if you have detectors at different positions, like different places on Earth, they're all going to see like a different density in the atmosphere. And if you just kind of normalize this to kind of how dense your atmosphere is, you can actually compare a lot better between different of these detectors. But if you kind of, you now know how much energy this shower dumped into the atmosphere, and from that you can calculate the energy. And what you do then is that some of the time you're going to have both this, what's called the surface detector, which are these water tanks or scintillation detectors, and these fluorescence telescopes. You're going to have them running at the same time. So some of the showers you're going to see with both. And so you can use these very accurate fluorescence telescopes to calibrate your surface detector. And so then if you have another shower during the day, you have calibrated your detector, and you can then also calculate the energy of the shower if you don't have the fluorescence data. And so if you do this a bunch of times and you measure how many of these particles do you get at what energy, you can draw the spectrum. So what this tells you is, so the further on the right you are, the more energy these showers have, and kind of the further up you are, the more of them there are. And if we look through this, we see a couple interesting things. So first of all, these energies can be huge. So this is something called a logarithmic scale. So if we go from kind of one tick to the next, this is an increase in energy by like 10 times as much. And so for comparison, the energies you can reach with particle accelerators. So this is for the Tevatron, which used to run at Fermilab. This is for the Large Hadron Collider in Geneva. So these are kind of like the biggest particle accelerators we have right now. They're down here, and we can see cosmic rays with energies almost 1 billion times that. The energies, they're measured in this kind of weird unit called electron volts. But at these highest energies, that is roughly the energy of a well-thrown baseball. I've been told, I don't know how baseball works, so for Europeans like me, it's also like a good serve in tennis, if the energy of the ball then. I also saw, like in a German article once, it compared to the energy of a kick in the butt. I don't know how they measured it, but don't ask me how they measured it. Okay, so something out there can produce particles with energies something like 1 billion times anything we can do here on Earth. So that alone, in my opinion, already makes them interesting. The next thing is that on this axis, this is also a logarithmic axis. So if you go from here to here, it's, what does it say? It's a factor 100, no, not even 100. It's like 10 to the 5, so it's a factor 10,000. So at these very low energies, they're actually pretty common. So here you have about, per square meter, you have 1 particle per second. And then if you go to higher and higher energies, at this end here, you have basically 1 particle per square kilometer per century. And that's why these detectors like the POG Observatory and the telescope array are so big, because you need a really big detector if you want to have a chance of actually seeing them. Now, because at the kind of lower energies, they are so common, you can actually do what Victor has more or less did. You can just basically put a particle detector in space if you want to detect them. So there's, for example, the alpha magnetic spectrometer that's just kind of on the outside of the International Space Station, and it's basically a particle detector that's just looking at whatever is coming in. Interesting is also Voyager 2 and also Voyager 1. They actually have little particle detectors on board, and they're kind of just making it out of the solar system, and they're still sending. Voyager 1 actually recently lost communications. They're trying to get it back, but Voyager 2 is still going strong. So we can actually measure what the particle flux looks like if you're kind of leaving the solar system. Or you can actually do what Victor Hess did back in the day and just strap your particle detector to a balloon. If you have a very high altitude balloon, the atmosphere up there is actually, the density is so low that you actually have a really good, like most of the particles are just going to reach your detector directly instead of colliding with the air before they reach you. So you can measure this directly, and having a balloon obviously is a lot cheaper than going to space. Now, the next thing about the spectrum I want to point out is it looks really boring, right? When we when we look back at like the spectra for light, we saw all these like absorption lines and emission lines and all that stuff. And here we see basically nothing, right? It's just a line going more or less straight down. There's 2 features here. There is something called the D, which is here, which is, if you look very closely, you can see that, here this line gets a little steeper. And then if you go here, this is something called the ankle, where the line gets a little less steep. But that's basically the only features we see. There is hints that there's a little change in the slope here, but it's really hard to see, and it's kind of just getting to the point where it looks significant. But overall, this spectrum just roughly follows what's called a power law. So the number of particles you see is proportional to 1 divided by the energy to the 3rd power. So 1 second. So if you have 10 times the energy, you have a little more than 1/1000th the number of particles anymore. There was a question, right? Yeah?
Yes. Where would the fastest particle that has ever been seen fit on this? Like at the very
Yeah,
end, or maybe even further along that scale?
Yeah, that would be roughly here. Yeah.
I was just wondering if it would have been even further or just there.
No, they're roughly here. Okay, so now we see this particle. The big question is, where do they actually come from? And what we can do is we take these particles and we just look at, what direction do they come from. And it looks like this, and it's not very spectacular. So you can see that, there's a little more particles coming from this direction than from that direction. But if you look at the relative intensity here, this is like a 1 in 1,000 difference. And if you kind of remove this kind of big structure, you see some smaller structure, but then the difference is even smaller, and it's all very uniform. So what does this tell us? Unfortunately, not a lot, because the problem is there's magnetic fields, and these are charged particles, so we're pretty sure they're some kind of nucleus from some atom. So they're charged, and I guess most people here are old enough to remember a time when not every TV was a flat screen. And back then, if you had a magnet and you held it to your TV, it would kind of mess up the picture, and you see these funny colors. And the reason is that in the back of this TV, there was a little gun that shot electrons at the screen, and if you had your magnet in front of the TV, then that would deflect these electrons, and they would just hit the wrong pixels, and that's why your picture got all screwed up. If you want to do this a bit more professionally, let's call it, you can get one of these. This is an electron ray tube that shoots electrons this way, and if you hold a magnet next to it, you can see that it's bent into this into a circle, and the radius of this circle is proportional to the energy divided by the charge and the magnetic field. So the higher the energy of the particle, the bigger or the less it's going to get deflected. But what that means is that all these particles, except for the very highest energy ones, are just going to get deflected by the magnetic field. So the direction that we see them coming from is not actually necessarily the direction that the sources are. And if you kind of, have a rough estimate of what the magnetic fields in the Milky Way are like, and you kind of model how they would move, it turns out most of them are actually going to get trapped in the Milky Way and kind of move all about, and they're not going to give you any direction information anymore. So maybe we have to look at other stuff. We can, for example, look at the composition. So it's some nucleus, but what element are they actually? Is this hydrogen? Is this iron? What is this? So if you have one of these detectors in space, that's fairly easy to measure. You just run them through a magnetic field, look how they're deflected, and then from that you can measure the charge of that atom, and then you have the chemistry. And so on the left here, this is from the alpha magnetic spectrometer. That was this detector that was strapped to the ISS. And this is how many particles of different elements they see. And a couple of weeks ago, we talked about the chemical composition of the solar system, for example. And you can see it's overall fairly similar. You still have more hydrogen and helium. But you see a lot more of these lithium, beryllium, and boron, right? We saw that these are extremely rare in the solar system in general, but they're pretty common in cosmic rays. And what we think is happening here is that you actually have heavier cosmic rays, and then while they're propagating, they're crashing into something, and that's going to tear this nucleus apart, and then you get, for example, lithium. And it's actually believed that a lot of the lithium we have on Earth actually came from these cosmic rays, from this spallation. But overall, it looks pretty similar to just the overall composition of the solar system. Now, this is at relatively low energies. If you want to do this at higher energies, you kind of have the problem that you can only look at air showers. Because if you have a detector in space, the chances of actually finding one of these really high energy nuclei are really low. So you want to figure out a way to measure the composition or figure out what kind of cosmic ray it was from the air shower. And you can actually do this because so these are two simulations here. On the left is from an air shower that was caused by a proton, so from hydrogen. And on the on the right is an air shower that was produced by iron. And what's happening is that if you have a proton, you have a single particle. If you have iron, you have 56 particles at once. And so if that crashes into something, this nucleus is going to get torn apart. So with a proton, in this initial interaction, you're going to produce like a handful of new particles. With iron, you have your big nucleus getting ripped apart, and you suddenly have a lot more particles in these first interactions. So because of that, these air showers from heavier elements are going to develop much quicker. And there's another effect that you can't see here because they're all simulated to start at the same position. But actually, because iron consists of 56 protons and neutrons, you actually have a target that's 56 times as big. So the chances of this initial interaction happening is much higher. So these showers are going to start much further up in the air. And also because a proton has a pretty decent chance to actually make it fairly deep into the atmosphere, where it actually has this first interaction is going to vary much more between different showers. So this is from a bunch of different simulations. So we just basically simulate a bunch of showers, and then we're just going to plot how deep in the atmosphere are they going to dump how much energy, right? Which tells us like how big is the shower at a certain depth. And the blue ones are for iron showers, and the red ones are for proton showers, for hydrogen showers. You can see the iron showers are all gonna develop much, or their maximum where they have the highest number of particles. It's something that's usually called X max. That's happening much higher in the atmosphere than for protons. And you can also see for protons, the scattering is, you have much bigger differences between showers than for iron. And so if you just kind of look at, at what depth in the atmosphere do we see the most particles, and you just look at, you make a histogram, you can see that for iron, they're all pretty close together and they're all pretty high in the atmosphere. For protons, they're all more scattered and they're much deeper in the atmosphere. And with these fluorescence detectors, we can see this directly, right? This is what these fluorescence detectors actually measure. They measure where in the atmosphere does the shower dump how much energy. And to come back to your question, about the size of the showers, that also depends a bit on the composition. So, I mean, you can kind of see it here. This shower is wider than this one, right? So what you usually have, you have this thing called the core, where you actually have a lot of particles that are within tens of meters. But then you have this bigger region that can be several kilometers wide, where you still have a lot of particles, but it's a lot less than kind of in the shower. So you will typically have a small region where you have a lot of particles, and then a much wider region where you get some. So yeah, one thing I could do is, I take my fluorescence telescope, I look at all these showers, I look where do we see the shower reach its biggest extent, and then from that we can figure out, are these particles on the heavier side or on the lighter side? There's a question.
Is there on one of those graphs, is that one outlier necessarily a proton or what?
So this is well, so this is from simulation, so we know that it's a proton because that's what we decided to simulate. You can just kind of have a proton get lucky or unlucky, however you want to see it, where it takes a long time until it has this initial interaction. So it kind of passes. It's just kind of lucky to not get hit earlier.
I was wondering if it was just somehow different.
No, you can actually have. There's some exotic particles that some theorists come up with that can actually cause showers much deeper in the atmosphere, and that's something people look for. But in this case, it's just a proton that got kind of lucky. Yeah.
Do the
No. No, I mean, that's why you have this fast development, because in the initial interaction, it's just going to get ripped apart.
So when you observe them through detector, how do you know that it was iron?
I mean, yeah, so this has to be some modeling. We know from accelerators we can simulate these interactions pretty well because, in this case you have your I don't know, nitrogen or whatever's in the air that the iron interacts with, that's at rest. And then you have a high energy particle slam into it. In a particle accelerator, you can just kind of slam two nuclei into each other, and that gets you an energy that's actually fairly close to what's happening in these air showers. So we can model it to up to energies that are fairly close to this. Okay, yeah. So we can measure this what's called a longitudinal profile of the air shower, and from that we can see if it's more on the heavy side or on the light side. But there's actually another way, and that brings us back to this muon, this kind of weird heavy electron that we saw earlier in the cosmic radiation. Because we actually know pretty well where these come from. Because if you have an accelerator and you smash particles into each other, you actually get a lot of these. Because if you collide, for example, two protons, one of the most common particles you're going to get is something called a pion. And they come in two varieties. There's charged ones and there's neutral ones. If you have a charged one, then what's going to happen is it's going to decay into a muon. And then this muon is going to also eventually decay, but at high enough energies, these can actually make it to the ground. And so this is a picture from this that's from something called a bubble chamber, which is fairly similar to a cloud chamber. And so that's what you can see here. From you have your pion here it decays, you have your muon, and eventually you can also see the muon decay here. Now, for this pion to decay, it's taking a little bit for this pion to decay. So if this happens fairly deep in the atmosphere, where the atmosphere is relatively dense, a lot of the time, this pion is actually just going to crash into another air molecule and then produce new particles. It's not going to decay, so you don't get a muon out of it. But if this happens higher up, where the air is a lot less dense, then this pion can actually make it much further, or it lives long enough to actually decay, and then you can actually get muons out of there. So if most of your particle shower happens high in the atmosphere, then most of the pions you produce are going to decay, you get a lot of muons. So that would be the case for iron. If you have a proton and your entire shower develops deeper in the atmosphere, where it's denser, then a lot of your pions are gonna collide with stuff in the air, and you're not going to get as many muons. So looking how many muons you get compared to all the other particles in the shower can also tell you something about where this shower happened. And then from that you can figure out what kind of element it was. And so if we do this, we actually see something pretty interesting here at the knee, where we saw this change in the shape of the spectrum, where suddenly our flux dropped off much faster. And this is actually not done with Auger and telescope array, because they actually need higher energies to see something. This is from another detector called Cascade Grande, which is in Karlsruhe in Germany. And if you look at the composition, so you cannot actually you can only get a fairly rough estimate of what type of element it was. So you can say, is it like a lighter element like hydrogen, or is it more on the heavy side like iron, or is it somewhere in between, like for example carbon? But this is kind of a family of elements that are roughly that mass. And what do you see there? So here, this is where the shape of your spectrum changes. And what you see happen at the exact same time is that suddenly your light elements, your hydrogen and your helium, disappears, and then it kind of comes back here, and your iron makes it to higher energies, and then it drops off. And so what we think is happening here is that you actually have two different compositions here. You have kind of two different types of sources, and one only can accelerate the lighter elements up to this energy. It can accelerate the heavy elements a little further, but only, not that much further, and drops off. And then you have another type of source that can produce higher energy, and that gives you back your hydrogen. And we're going to talk about a little bit more about where this comes from next week, when we actually can figure out a better picture of where these cosmic rays come from. Now, if you go to even higher energies, so this is with Auger again, you can see the same thing. So this is showing for different energies the kind of how deep in the atmosphere your shower maximum is on the left, and on the right it shows you, depending on the energy, how much variation you have with where your shower maximum is. Because if you remember, your lighter composition will cause your maximum to be deeper in the atmosphere, and it's going to cause you more variety. So you expect it. So this line here tells you what you would expect for if it was all protons. This tells you what you expect for all irons, and then the different lines are just different ways you can model this. And you can see that for a long time it looks like it's fairly light, and then suddenly it looks like it's getting heavier. And you see the same trend if you look at the variation between showers. So even at this very high energy cutoff, you also see this picture that our composition seems to get heavier. And now, because we think we have these two types of populations, we're going to worry about the lower energy ones next week. For the higher energy ones, what you can actually do is, because how much your cosmic ray is going to get deflected is going to depend on the energy. So if you only take the very, very highest energy cosmic rays, you can say, well, they're probably not going to get deflected as much. So maybe if you look where they're coming from, we get a rough idea of where they're coming from, like where the sources are, right? There's probably still some connection between the direction that the sources are in. And if you do this, so this is with Auger for the very, where you only take the highest energy ones, you get a map like this. So you have this big hole here, that's just where Auger can't see because the Earth is in the way. You can see that there's more cosmic rays coming from this one direction, and overall it's still fairly similar everywhere. So this difference is not actually too much. Another interesting thing you see is this gray line that I hope you can see here. That's where our galaxy is. And you see there's basically nothing, there's no association with where our galaxy is. And so if most of the sources were in our own galaxy, then actually, because our galaxy is fairly close by cosmic standards, actually we would expect to see most of the cosmic rays to actually come from this direction. And because we don't see this, we can conclude that at least at these very high energies, most of the sources have to be extragalactic. Unfortunately, you have this big blob. It's kind of hard to say for sure if there is, you cannot point to one specific source directly there. But there is actually, interestingly, there's a really good source candidate just in that just where we see the most cosmic rays coming from. And that is this thing called Centaurus A, and that is one of these quasars that we talked about last week. It's not actually technically a quasar because in this case you can see the jets are not pointing at us, but it is in radio. This is actually one of the brightest sources we can see. It's fairly close, so it is a really good candidate to be one of the sources of cosmic rays, and it's in the direction where we see the most cosmic rays coming from. So it is an interesting thing. It's hard to tell if this is a coincidence or not. I see some questions. Yeah.
Could it have something to do with the fact that I just saw this somewhere, but could it have something? Could this be some interaction between normal matter and dark matter that we don't usually see? Because I've seen at least two places galaxies form because of blobs of dark matter.
Yes. So this was actually a really popular theory for where they came from in, I think, the 90s or 80s. There was this idea that you could have these really heavy dark matter particles, and if they decay, they would produce something, they would produce these really high energy particles. The problem,
Theory to the opposite of what I'm saying.
no, I mean, it would, wasn't your idea that cosmic rays would come from dark matter?
I said that it could have something to do with like the cosmic rays somehow interacting with dark matter and deflecting away from us.
Oh, not with dark matter, but something similar. And we're going to get to that in 2 weeks. But yeah, so there was this idea that cosmic rays might come from dark matter. The problem with that is, like, we know that at least a big part of the cosmic rays have to be heavy nuclei, and you wouldn't get that from a dark matter decay. So that's why this theory is not really popular anymore. But there are actually interactions between cosmic rays and the cosmic microwave background, interestingly, that we're going to get to in 2 weeks. Yeah.
Looking at the directions you're talking about and thinking back to the Compton lecture in 2019, is the source of the cosmic waves also similar to the source of the gravitational waves?
Maybe. So there are, I was going to talk about the next week. But there are these things called gamma ray bursts, where you just see a bunch of gamma rays suddenly coming from somewhere. We don't really understand we think most of them are from basically from a supernova, where you have an extremely heavy star collapsing directly into a black hole. But thanks to LIGO, there was one collision between neutron star that LIGO observed, and then basically told a bunch of telescopes, like, hey, there's something interesting happening, look there. And we saw a gamma ray burst from that. So we know that this can cause these gamma ray bursts. It's probably like a subclass of gamma ray bursts. And there are ideas that because if you see gamma rays, there's probably some cosmic rays there. So this is probably one possible source of cosmic rays, but probably not the highest, at the highest energies. It probably cannot accelerate particles all the way to there. Yeah?
So, aren't there cosmic rays coming from a lot of places throughout the cosmos? And the question that you're addressing here is, which are the ones that are hitting, that we can detect, that are coming to us? And for that, is there a upper limit to how far away we can detect the cosmic ray from?
Probably yes.
Does that give you a sort of an order of magnitude idea of how many sources there can be?
Yes. Let me get back to that in 5 minutes. Okay. So we have this one source that's probably, like, it is at an interesting position. Now, what would be really interesting is if out of all these cosmic rays we see here, we could only pick out the very lightest ones. We could identify this cosmic ray as iron, so that probably gets deflected quite a lot. So we're not going to take that one, but if we see something that's probably a proton, that's going to give us a much better picture where our directions are. So because of that, the POG observatory now has this upgrade where, in addition to this water Cherenkov detector, they have one of these scintillators on top. And with this, you could actually measure, like, you could identify muons separately from all the other parts of the shower. So with this, you could actually, for every event or for every cosmic ray that Auger sees, you could get a good estimate of what the chemical composition is, and then you could pick out your lighter elements, and then hopefully this picture gets a lot better. But that's currently being built, and then it also is going to take a while for them to see enough cosmic rays to actually do this. So I'm going to leave a little bit on a cliffhanger today, and to kind of spoil the surprise a little bit, we actually don't really know where cosmic rays come from, the very highest ones. We have some decent ideas, but if we just look at cosmic rays, we cannot actually say a lot right now. So, okay, we know that at low energies, they're all coming from pretty much the same direction, so they're probably getting trapped in our galaxy, because that's also what you kind of expect if you have a rough estimate of what the magnetic fields are in our galaxy. So lower energies, they're probably from our galaxy. At the knee, so at this one point, we see both a change in the spectrum, the shape of the spectrum, and in the composition. So we think this is probably where the source types change from galactic to extragalactic cosmic rays. We also see this heavier composition at highest energies, where it's hard to say where this is coming from. There's kind of two different ways this could happen that I'm going to get to eventually. And even at the highest energy, it's pretty close to us seeing the same number of cosmic rays from different energies. And that's to come back to the question earlier. That tells us this cannot be, like, there is not one very strong source that's nearby. So it's probably many sources that are a little further away, and they're all individually fairly weak. But for now, this is kind of where we are, if we just look at cosmic rays. But fortunately, there's different particles we can look at. And next week, we're going to talk about gamma rays, which is technically light, but it's acting very differently. And for that, we take telescopes like this, and we're going to get to that next week.
Can we say approximately how many different sources of cosmic rays? There's dozens, 50, there's hundreds.
There are estimates. I don't remember the numbers, but I think it's at least like several dozens, probably more like hundreds.
Several dozen.
Yeah. Yeah.
You know, I worked in research in electrostatic painting, and we use electrode 100 kilovolt to generate high electric fields. And within that zone of where the electric field exceeds 310 to the power 6 volt per meter, that's where the air gets ionized, and that we generate the ionization to charge the paint. Then came to my mind, if I have one electronic charge, which is 1.6 10 minus 19 coulomb, how much electric field it would generate within the space. And I found out, I made the calculations, that it's a distance about 22 or 28, I don't remember exactly, 22, 28 nanometer. Within that radius, that charge, the electric field would exceed the ionization of the air, okay? So, also, with research and reading, they say that every cubic centimeter of air on Earth, it has 400 free electrons, 700 negative ions, and 1100 positive ions. So it is really neutral, but there are so many ions there already within a cubic centimeter. So if we have 2200 ions, okay, including the electrons, within a cubic centimeter floating around, and each one has a zone around it that exceeds the ionization of the air, okay, the condition. And if they get close to each other, they can ionize each other. And is it possible that all this ionization that we are detecting is really happening in front of us in the air, okay, and we are not really looking there? Is it possible that all this ionization is normally happening in our air without the need for cosmic rays? Maybe we are only accusing the cosmic rays.
I mean, so there is some ionization happening that's not cosmic rays, yes. But I mean, we have other methods of seeing cosmic rays. There are other particle detectors that do not rely on ionization. We see them there too, and you know that would be independent of this ionization. So there's independent methods of seeing these cosmic rays. Yes. Yeah.
So you mentioned that we cannot figure out the direction because of magnetic field. How likely is a cosmic ray to encounter magnetic field? Isn't magnetic field just close to all the matter and most of the space is empty?
Well, so this is the other big problem. Measuring magnetic fields is really, really hard. So there are, you can really only measure them in some like very specific circumstances, and then you have to kind of, you know your magnetic field in certain positions, and then you have kind of to figure out what the magnetic field is probably like in the rest of space. And that's really hard. So we are pretty sure that there are magnetic fields like even between galaxies, but how how strong they are is really, really hard to say. And that's one of the big problems. Like if we actually knew the magnetic field, we could just trace back where they came from, but we don't.
Actually, that reminds me, yesterday's New York Times has a graphic of a magnetic field far into the space. I don't know how some people do it.
Yeah, within the galaxy, it's easier because we know where matter is, and it's, you can measure it from. There's some ways to measure magnetic fields that work better if you have stuff there. So for the galaxy, we know it a bit better. I wouldn't say it's really good, but once you're out of the galaxy, it's pretty badly constrained. Unfortunately, otherwise this would be a lot easier. Yeah.
So I have a couple of questions related to your very first slide and another one. So the cloud chamber. So going to the first slide, you have the
this one?
ionization
Oh,
of a single atom. And what I'm trying to put my mind around is the relationship of all of this that you've explained about cosmic rays to the fundamental ideas of quantum mechanics itself. So that looks like a Bohr atom before the development of the full development of modern quantum theory. And my understanding of that, which came up a dozen years later with Schrodinger and those guys, was that on the basis of the principle of superposition, there is no billiard ball type electron there, and it has no particular position. Its status is a superposition of all possible outcomes of observation. And so the first question I have is, when that photon comes in, all of a sudden now you're jumping from that model to a billiard ball model, and it somehow involves what this mysterious process that Bohr called wave collapse, and many other people later have different ideas. The last one I ever read about was decoherence of the wave function. And so the question I'm asking really is, when that happens, how does that happen?
Okay.
The photon comes in and it hits a cloud of probability and produces a particle.
Yeah. So this picture is, as you said, it's based on the Bohr model, where you have like your nucleus in the middle, and then you have kind of these orbits that are a little like planetary system. That's like way out of date. But what you still have is your electrons are going to have like well-defined energy states. It can be in several energy states at once because of superposition, but most of the time it's basically going to be just in one.
Isn't the superposition also applied to its location? It's in all.
Yes. So if you wanted to draw this correctly, you would not draw these orbits. You would draw kind of the probability for the electron to be in a certain position. Yes, that's true. Now, the way that this interaction happens, if you want to go really into detail, is they're not going to like directly bump into each other. they're going to exchange a photon between them, and that's going to transfer momentum from one of the electrons to the other one, if you want to get the detailed explanation.
The question on the cloud chamber is, it's sort of related to that because it has to do with position. And I seem to remember having read somewhere in one of my many readings by scientists for people like me, is that each one of those lines, or the other pictures where you have the curved pictures, each one of those it's a series of discrete interactions between one entity and another, and the theory itself, because of this cloud probability, never says really where any particle is. And I think I read somewhere that as a matter of pure theory, you cannot even say, the theory doesn't say that it's the same particle causing each of the successive lines, and that almost comes out of some non-observable assumption that, well, the most plausible thing must be that it's caused by the same one. But so am I incorrect in understanding that as a matter of pure theory, you cannot say that that's the same particle causing each of those distinct
Yes, you are correct, but you're also going really deep into quantum mechanics that I tried to avoid. So there is this thing in quantum mechanics that says that two particles of the same type are fundamentally indistinguishable. Like there is no way to say, like if I have one particle here, I have one particle here, let's say the electrons, there is no way to tell me that like 5 minutes from now they haven't switched position. If you kind of go through like all the ways you could come up with to figure out that they're like still the same, you could for all of them you could find other ways that they wouldn't work. So if you want to go into like really deep into theory and do this completely correctly, what you would actually talk about is, for example, this muon it's not a muon particle. You have a muon field that basically is a field that describes kind of all the muons in the universe, and then this is one specific realization of this field, basically. It gets really abstract, but this really only, like this effect of indistinguishable particles really only shows up in practice like under very specific circumstances. So effectively, like a lot of times, it is easier to just think of this as being a muon, and it works. So it is, you're right that it is to some extent a simplification, yes.
Can I have one more question?
Sure.
So am I correct to understand that the upshot of what we've heard here today is that I could conclude that the entire universe is awash with all these cosmic ray particles everywhere, and the intergalactic, within the galaxy, in free space, everywhere we have these particles, and if so, what's the volume density of these particles? Let's say how many per cubic meter? Is it a gazillions, or
So I don't remember the number, but hang on, we can do some back of the envelope calculations. Okay, so if we go to this energy, we have like 1 particle per square meter per second. So that means you have, you put your area of 1 square meter there, you have 1 particle going through there per second. Now if you stretch this out into a cube, then that would mean that on average there's less than 1 cosmic ray in this cube because they're going at the speed of light, right? So you could calculate it, but it's fairly empty still. Like you're not like, it's going to be less than 1 per cubic meter. I would have to start doing math in front of people now to give you an exact number. I would prefer not to do that.
this would be true throughout the universe?
Well, it's probably not. There's probably a lot more cosmic rays inside of our galaxy than in extragalactic space, because the lower energy galactic cosmic rays are probably getting trapped inside the galaxy mostly. So it's probably not the same everywhere.
So not that many.
Yeah, and so like this very, very low energy part here, like we know exactly like this is from the sun, because you see these what are they called, like solar winds. You can measure this directly. You can see polar lights. Like the very low part. Yeah, we know exactly where this is coming from. It's kind of like all this part. I want to think someone first for who I didn't. Yeah.
Okay, so there's these muons that are created by the cascade of the cosmic ray particles. How many muons will you likely get from one cosmic ray particle? Depends on the energy, I understand.
Yeah, I don't remember the number, but it's definitely in the millions.
Maybe thousands, or
It's in the millions, definitely.
Millions
Yes. Like
cosmic
at
ray
these.
particle of muons, and a good percentage of them strike the Earth, and some go underground.
Yes.
Right? Some penetrate underground, and they come in from all different angles, basically.
Yeah.
There's kind of a smoothing process, I guess. Now, most of them come in from around the poles, and then they get redirected by the Earth's magnetic field.
Well, so these.
I missed the very early part.
Oh, so the Earth magnetic field only really plays a role kind of at the lowest energies, because at the highest energies, the deflection.
It comes straight through, pretty much.
Yeah, it's the highest energy, yes, and the muons only get produced in the inside the atmosphere. So there, the deflection is there, and it's you can see it. There's something I didn't get into today. You can also detect these cosmic rays through radio signals. They also produce radio signals, and that is actually because of deflection in the magnetic field of the Earth. So there is a little bit of an effect, but it's pretty small.
So the radio signals from them, that's kind of like a static, I guess.
It's like a very short pulse. Yeah.
I don't know if this has any relationship to cosmic rays, but I just heard this last night on an astronomy program, so I memorized it, that in our Earth's atmosphere we have 100 trillion atoms per cubic meter. Then they go between stars, between galaxies, it's only 10 atoms per cubic meter. But I don't know if there's any relationship to cosmic rays based on that.
Most of those are probably not cosmic rays now. Yeah.
Quantum mechanics and quantum particles. I believe that mechanics really should be related to mechanism, to interaction. Okay, and quantum particles are tiny particles. Sometimes they call it, the photon is a quantum particle or muon or whatever it is. Shouldn't really we distinguish between the two and use them correctly? So in this case, quantum mechanics is a mechanics like Newton mechanics, okay? And not confuse the two with each other.
I mean, one is usually called classical mechanics and quantum mechanics, so there is a distinction. Yeah, I mean that's the word that stuck like 100 years ago, so I guess it's too late to change it now. And yeah, I mean they're different, but it's it's naming. You can discuss forever.
But when you are physicist or scientist, you should distinguish.
Yeah.
You should not confuse the two with each other. Okay.
Yeah,
unless it becomes afterward becomes like a snake oil. Okay.
Well, I mean, as long as you're honest with what the word means, I think it's fine. It is a name. It has a certain definition, and I think that's true. Yeah.
Question: cosmic rays. You're looking at the particulate. It's very distinct from gamma rays or gravity waves, which are massless excitations. These are all excitations of fields. But you see mostly protons, and that hits things and makes other stuff like muons. They all have different lifetime. proton doesn't decay. You've never detected it. So it's stable. So you see mostly protons. And iron is fairly stable. So you see a lot of iron. Is there any of the other things, or does it all decay away?
I mean, you have most elements, unless you get to the the really heavy stuff, have at least one stable element, or a stable isotope. Sorry?
Primary cosmic rays. You see muons
Yeah.
secondary.
So, okay, there is actually a really interesting thing that I didn't quite have the time to get into. But so AMS can actually not only measure like different atoms, it can also distinguish between isotopes. And there is actually, so especially like beryllium, there is, I think it's beryllium 10 and beryllium 11 that are, one of them is radioactive and will decay after, like, I think it's like in the millions of years. And because what probably happened, so the region where these cosmic rays are accelerated are, they're probably a lot denser than like the average galaxy.
Well, it's longer lived because of relativistic time dilation.
Yes, that also happens. But like these interactions that, where some carbon or whatever collides and gets split into beryllium, that's probably happening close to the source. And so what you have it's kind of like carbon dating, where you have this atomic clock from the decay. You have your radioactive beryllium probably getting produced close to the source. And then from just looking at, how much of this radioactive isotope compared to its decay products do you see, you can get an estimate of how long the cosmic ray actually traveled.
That's interesting.
Yeah.
Now you can profile sort of where sources are from the time dilation and their energy.
Yeah. Yeah, that is actually another reason why we think these are from the galaxy, because any extragalactic source that's a good candidate is so far away that beryllium wouldn't live long enough to reach us.
Muons directly.
No, I mean muons they would decay way earlier. Yeah.
In this chart over here, and the vertical line here, is that the mass, or is it the number
Which one?
of atoms?
This one?
No,
Oh,
the
this?
chart on the right.
Oh, this?
Yes,
Like this?
the vertical line here.
Yeah, this is how many you see.
Is it how many atoms or how much mass?
This is number of atoms.
Number of atoms.
Yeah.
And each atom, like if you take the iron is 56 times in mass the hydrogen. So if you want to convert this to mass, in this case the hydrogen should go even higher.
Well, not.
And the iron should go higher, and the hydrogen will go down.
Yes, but it's a really tiny effect because this is a logarithmic scale. So if you go from here to here, this is like 10 times as much. So from where's iron? Iron is here. So you're at 10 to the 7 to 10. So this is like almost 10,000 times as much hydrogen than iron.
I know, but the chart is going to be changed.
Yeah, it's going to be changed, but a little bit. Yeah.
Not a little bit, 56 times.
Yeah, I mean, yeah, but
Between iron and hydrogen.
yeah, but I mean, hydrogen is still much more common, and it's it depends on how you want to count. Okay, I don't think I see any more questions. Otherwise, last chance. Okay, then see you next week.